Good morning, B&G 312 class. I hope everyone had a decent spring break. Happy snow day. Here we're going to talk about the first of two lectures on heterogeneous reactions. Hopefully we will meet on Wednesday for the second part, but here is the first part recorded for you. First, some notes. The metabolic flux analysis homework that was assigned before spring break is due on Thursday, the usual time. And as it turns out, Friday, if you were there on Friday, the 11th, that was Socrative bonus day. So each correct answer you gave on Socrative that day is going to be worth plus 2 points on exam number 2 for a maximum of 10 because there was 5 questions. And each incorrect attempt still gets some points with plus 1 on exam 2. So the maximum you could get doing these Socrative questions on Friday the 11th was 10 points. So that will hopefully help some of you. And as a reminder, speaking of exam number 2, it'll be Wednesday, March the 30th. So a week from Wednesday. And topics to consider, speaking of metabolic flux analysis, will be Wednesdays and Fridays before spring break, and this week's lectures. If there's going to be anything on the exam, it'll be those things. Heavily those things. So if you're going to study anything, study those topics in those lectures. But there will be old exams and a list of topics of which to study will be available sometime this week, hopefully by Wednesday. Alright, so let's talk about heterogeneous reactions. What are heterogeneous reactions? They are reactions that occur in the presence of significant gradients, concentration gradients or temperature gradients. Concentration of what? Well, we're talking about enzymatic reactions, so the concentration of substrate. Concentration gradients are the most common. And for the next 2 lectures, we're going to focus on those. Concentration gradients of substrate are common when reactions involve things like immobilized enzymes, enzymes that are stuck to some sort of substrate. So, biocatalysts, as we've talked about before, when we talked about animal and plant cells, immobilize themselves naturally. Cells will flocculate together, forming a big clump. Microbes can form biofilms, and we will talk about diffusion of biofilms on Friday, and can adhere to surfaces. Tissue engineering, cells will attach to scaffolds. Bioremediation, microbes will attach to the soil. The soil is highly charged, so it will attract microbes, which acts as sort of an immobilizer in and of itself. And industrial bioprocesses, as we've gone over, especially with one mass balance, we've talked about cells or enzymes that are artificially immobilized, and that sort of thing happens all the time. And we're going to focus on that for the next couple of lectures here. Okay, so then, like I mentioned before, a couple of weeks ago, there are many ways in which we can immobilize enzymes. There are irreversible methods where we can immobilize the enzyme and it's stuck like that. So things like covalent binding, entrapping in beads or fibers, encapsulation in some sort of polymer, cross-linking them all together. And then there are the reversible methods, which are adsorption, which we could easily desorb enzymes if we wanted to, ionic binding, affinity binding using antibodies, chelation or metal binding, and disulfide bonds. So you can do this irreversibly or reversibly. And given the situation, one method might be preferable to the other. Alright, so there are advantages and disadvantages, of course, as in everything else. There's advantages and disadvantages of immobilized catalysts. So the advantages, one of the big advantages, is that you can reuse the catalyst. You know, we can flow our substrate plus buffer or growth medium or whatever through a column packed with immobilized biocatalysts, and we can continue to reuse the catalyst for a lot longer than, say, we could if we were using live cells. It's easier reactor operation. Continuous culture or continuous bioreaction is much easier to attain. Easier product separation because we don't have to separate the product from the enzyme. And we can have a wider choice of reactor. And we can even have some fancy reactors where we look at the immobilized catalyst separated from everything else. Disadvantages could be immobilization could cause loss or reduction in activity. There is that diffusional limitation, which is the whole point of what we're going to talk about today. And of course, doing all this stuff, immobilizing catalysts, the raw materials, the process, that is all an additional cost. So you've got to kind of weigh the pros with the cons to determine if immobilized biocatalysts is the right option for what you want to do. Some examples include the removal of lactose from milk. So we have beads, polymer beads, with immobilized enzyme called lactase. And we run the milk through a column filled with these beads. And the lactase cleaves the sugar and converts glucose to galactose, or converts lactose to glucose and galactose as the milk flows through. And then you have lactose-free milk coming out the other end here. It's also used in bioremediation of biodiesel production, where ionic liquids are used to absorb a lipase, where we can add alcohol and a fatty acid or a fat and convert it to biodiesel plus some glycerol. And then, of course, other applications for immobilized biocatalysts, immobilized enzymes like molecular biology, microelectronics often will include things like biosensors and other immobilized enzymes, all of which are pretty neat to think about. But there's many applications for immobilized enzymes. So microbial cells and enzymes can be immobilized by entrapment within a matrix, which means they are stuck in there, they are immobilized, and things like alginate or agarose are common matrices. And they are good because they're generally inert. They won't react with anything or with nothing to speak of necessarily. And they allow diffusion into and out of. So it's pretty good if you want to immobilize cells or enzymes using this method. And then there are also porous solids that can be used where we entrap cells or enzymes in pores. As you can see here, they can be entrapped in solids like ceramics or glass. These are common beads that are used. And they have a lot of surface area in the interior, and you can trap a lot of enzymes and or cells in there and immobilize them in that way. But with either of these things, substrate must find its way to the biocatalyst for the conversion to take place. Thus, the concentration gradient that we spoke of when we first started here is going to inevitably be created here. So what do we think about when we think about concentration gradient? So namely we're thinking about a spherical catalyst, these beads that I've been talking a lot about. And you have the concentration of substrate in a bulk liquid containing these beads that have the biocatalysts immobilized either on the surface or in the interior. And the concentration of substrate will vary in the bulk liquid as compared to in the catalyst itself. And you can see this graph here associated with this spherical biocatalyst schematic, where we have first a layer, kind of like our boundary layer when we were thinking about viscosity and mixing. We have a boundary layer of similar status here with the biocatalyst, which is poorly mixed, and there is a bit of mass transfer effects going on here. And we see there's a decrease in the substrate concentration as we go from the edge of the boundary layer to the surface of the catalyst. And then also as you get into the catalyst, as you're going towards the center, there's less and less concentration of substrate as you go to the center, and then and the concentration increases as you get towards the surface on the other side. The transport of the substrate across the stagnant boundary layer, the poorly mixed boundary layer, is known as external mass transfer, of course. The transport through the solid catalyst is known as internal mass transfer. And you can have several different types of gradients that surround or penetrate spherical catalysts, depending on what we're looking at here. Depending on the nature of the substrate, the nature of the biocatalyst, the nature of the bead that you're using. So the first one here, A, we see the substrate concentration goes all the way down to 0, and you get a dramatic decrease of concentration as you get towards the surface of the catalyst. The substrate here is consumed completely before reaching the center of the catalyst, so it might be a pretty active reaction here. For part B here, we have substrate that is preferentially distributing to the solid catalyst. This could be you have a solid catalyst that is, say, hydrophobic, and your substrate is also hydrophobic, but it is in an aqueous solution. It would preferentially go to the biocatalyst, which might be advantageous depending on what you're trying to do. Substrate can preferentially distribute to the bulk liquid, and you have say a hydrophilic biocatalyst, but your substrate happens to be hydrophobic. So you get a sharp decrease in the concentration of substrate in your biocatalyst itself. So this leads us to talk about true and observed reaction rates. So we can observe a reaction rate here, but we also would want to know the true or intrinsic rate of reaction. And because concentration rates vary in these catalysts for the diffusion problems that we just saw in the last slide, as well as other things, other aspects, the localized rates of reaction are also going to vary. You have the true rate of reaction, which is the local rate of reaction, the rate at or beneath the surface of your biocatalyst bead. That, of course, is difficult for us to measure. We can't just put a probe, a small probe, sticking into each and every one of our catalyst beads. The observed rate is what we're really going to have to lead with here, and that is the rate of disappearance of substrate in our bulk liquid. So this stuff in bulk liquid is not even close to being associated with the catalyst yet, because it's got to traverse that boundary layer and then penetrate the catalyst. But that is relatively easy to measure, and that's where we will start. So how do mass transfer and reaction influence the observed reaction rate? Is the observed reaction rate a result of, say, slow mass transfer, or due to a slower rate of reaction, perhaps? Mass transfer limited reaction, otherwise known as diffusion limited reaction, the ability of whatever substrate you're using to reach the catalyst is significantly affecting your rate of reactions. That is mass transfer limited. Rates of reaction and mass transfer are not independent in heterogeneous reactions that we are going to discuss. So we think about diffusion through our spherical catalyst in terms of how it diffuses to the center. We can look at different spaces within that catalyst, a space or a shell called delta R here in this case, and we can take the steady state shell mass balance. So we imagine this shell, which has that radius delta R that I just mentioned, inside a spherical biocatalyst. The substrate will cross this shell, or must cross this shell, in order to reach the center of our catalyst here. So that's kind of the goal, is to reach the center of the catalyst if you're a substrate. You're going to react a little bit along the way if the catalyst is evenly distributed throughout the biocatalyst bead. But to think about traversing that shell, we can think about the center of a turducken, where we have to cross the shell of some delicious stuffing in order to get from the turkey to the duck to the chicken in the middle. So we have R as our maximum radius of our bead, And little r is the radius inside the particle where we are estimating here. So that's how we can keep the two radii straight. And of course, mass balances are your usual mass balances. We've been talking about those since the beginning of class in January. So we make certain assumptions, however, in order to apply our mass balance equation to the steady state shell mass balance problem. We assume that the particle is isothermal because temperature changes can certainly affect diffusion, and it is much simpler to assume that we have an isothermal thermal particle, and we usually do. Maybe in rare cases we don't. Mass transfer will occur by diffusion only. It's not occurring by convection, so only by diffusion. Diffusion of the substrate through the particle or the polymer or what have you itself. And diffusion can be described using the Fick's law, which we've talked about at length, with what is known as a constant effective diffusivity. And we'll talk a little bit more actually about effective diffusivity. We've already touched upon effective diffusivity in several other cases, like diffusion in the body, for example. And we're assuming the particle is homogeneous. That may not necessarily be the case at the molecular level, but for us we assume that it is homogeneous. And this, you're going to see, is a little bit different than how we would estimate diffusion effects in biofilms, which we will get to on Friday. The substrate partition coefficient is unity. I'll explain that more in a little bit. And the particle is at steady state. So for a lot of this stuff, we are assuming steady state. It's in the name, steady state shell mass balance. So we're assuming that particle is at steady state. Then the substrate concentration varies within a single spatial variable here, which makes the whole thing work to begin with. It's something we kind of tacitly assume usually here. So let's first talk about effective diffusivity again. Diffusion is taking place through a non-homogeneous medium, and I told you to assume that it is homogeneous, and that is true. We are assuming that. But we could be looking at a spherical particle that has pores that contain immobilized enzyme or cells. That's not homogeneous. So we need to consider the effective diffusivity. The reactants in the bulk solution must travel further, given that the pores in the bead are not straight. Diffusion also takes place in a smaller area, i.e. inside the pores as opposed to bulk solution. These effects are taken into account by defining a term known as effective diffusivity, and you can see it right here, where DAE is the effective diffusivity. This term is the particle void fraction, and the tau is the tortuosity, which is crudely represented here by these red arrows, the path that substrate must take if we're talking about a spherical particle that has, or any kind of particle that has pores in it. It must traverse those pores. So back to the assumption. Why these assumptions? Let's just unpack that a little bit more. The particle is isothermal. Well, the parameters like reaction kinetics and concentration, like I mentioned, vary with temperature. So we have to consider that. And mass transfer occurs by diffusion only. Otherwise, it violates our term number 4 here, our assumption number 4. But we're assuming essentially that convection through pores is negligible here. And that's probably pretty much true since the pores are so small. Diffusion can be described using Fick's law with constant effective diffusivity, assuming the effective diffusivity does not change with its position and is independent of substrate concentration here. The particle is homogeneous. We're assuming uniform distribution of enzymes or cells throughout the particle. The substrate partition coefficient is unity. This is valid for most substrates, so this is not a stretch here that the partition coefficient be unity. And the particles at steady state. That assumes there's no enzyme inactivation, there's no cell growth, or any cell differentiation. Everything is basically the same here. You have active enzyme, or as active as can be. If you have cells, they're not growing cells, they're immobilized, they're staying put, they're not dividing, they're not differentiating, they're not turning into other types of cells here, which is possible if you're not immobilizing them. But we're assuming none of that is happening, so the particle is at steady state. And substrate concentration varies within a single spatial variable. We are assuming that substrate diffuses through pores towards the center. We're assuming it's going towards the center. So here's an example. We have a concentration profile for an immobilized enzyme, and the kinetics of this are first order. We have the enzyme is immobilized in 8 millimeter diameter agarose beads. The concentration is of protein or of enzyme is 0.0032 kilogram protein per meter cubed gel. 10 beads are immersed in a well-mixed solution containing 3.2 times 10 to the negative third kilogram per meter cubed substrate. Effective diffusivity of substrate is 2.1 times 10 to the negative ninth meter squared per second in the agarose gel. And its first order kinetics, our rate constant in this case is 3.11 times 10 to the fifth per second per kilogram of protein. Mass transfer effects outside the particles are negligible, and we are wanting to know what is steady state concentration profile as a function of particle radius. So you can assume that we will probably have to be drawing a graph by the end of all this. So let's get there first. What do we know? The max radius of our agarose bead, our big R, is 4 millimeters. We said the diameter was 8 millimeters. Concentration of substrate in bulk solution is 3.2 times 10 to the negative 3 kilograms per meter cubed. Our effective diffusivity is 2.1 times 10 to the negative 9th meter squared per second. Our rate constant, 3.11 times 10 to the fifth per second per kilogram. And we want to know the steady state concentration of substrate, or Ca, as a function of the little r particle radius. So sadly we won't be able to do the Socrative questions today, as I'm recording this and you are not yet watching it. The max radius of the bead is 4 millimeters. We have our concentration of enzyme. What is the volume per bead at the max radius in meters cubed? And then what is the amount of enzyme per bead? And of course we would use our volume of a sphere equation here to determine that our volume per bead at max radius is 2.68 times 10 to the negative 7th meters cubed. The amount of enzyme per bead, if we multiply the volume of the bead by the concentration of enzyme, we would get 8.58 times 10 to the negative 10th kilograms of enzyme per bead. And then we've calculated that, and now we want to know what the rate constant is. We already know the rate constant in per second per kilogram, but we have our kilograms of enzyme now, so we want to determine our rate constant in per second. So we have 3.11 times 10 to the fifth per second per kilogram. So we will just multiply that by our amount of protein or amount of enzyme per bead and get 2.67 times 10 to the negative fourth per second as our K1, our rate constant, our first order rate constant. Okay, so the intraparticle substrate concentrations can be calculated as a function of the radius big R, also the radius little r as well, using this equation here below, this fairly complicated equation here. And we can first determine this inner term here with the r square root of the rate constant divided by the effective diffusivity. And if we're looking at this term here, the bottom term, the value for that is 1.43. And then we can take our sine h, or our hyperbolic sine of this value, which is calculated in this way, and get 1.96. So we can also do that for the top term here. and then the rest of it is fairly simple. So we figured out that term here, the sine h of this. Now we need to do the same for this. So we have an r, a little r, at 2 millimeters. We have our K1, our first order constant, our effective diffusivity. So we should be all set. We just have to keep track of our units and figure out what the top term is. So we can take that value, plugging in all the numbers here, changing our units, and we get 0.71, and the top value is 0.77, or it ends up being 0.77. This should actually be a little r, not a big R here. Okay, so we have these things. We have our top and our bottom term for this ratio here. We know our big R, we know our little r, we know our concentration of substrate in bulk solution. This should be a straightforward thing. Just plug in everything and solve to get our Ca, our concentration of substrate in the particle at 2 millimeters, our shell concentration, and we get a concentration of 2.5 times 10 to the negative third kilograms per meter cubed here. So we can do this, we can do exactly what we just did for several radii here. So for several r's, little r's, we can go from 0.005 times 10 to the negative third all the way up to the surface of the shell, of the bead, the particle, and get a variety of concentrations here. And then plot them and show our profile, our concentration, a substrate concentration profile, as you get closer and closer and closer towards the center of that bead. Now let's take into account zero order kinetics. We already did our first order kinetics. What happens with zero order kinetics? Well, the hallmark of zero order kinetics is that substrate has to be present in order for the reaction to go. If there's no substrate, there's obviously going to be no reaction. So if we have no substrate in the middle of our particle, we get no reaction here. So the rate constant is irrespective of the substrate concentration. It just has to be present. So that's the hallmark here. So let's look at an example with zero order kinetics in spherical particles. So we have non-viable yeast cells. We talked about non-viable cells a while ago in one of our mass balance classes. Here are non-viable yeast cells that are immobilized in alginate beads. These beads are stirred in a glucose medium under anaerobic condition, and the effective diffusivity of the glucose in the beads is dependent upon the cell density according to this relationship here. The effective diffusivity equals 6.33 minus 7.17 multiplied by the yeast concentration, the weight fraction of yeast in that gel. And it should be noted that the DAE, or the effective diffusivity, is in terms of 10 to the times 10 to the 10th meter squared per second. So let's figure this out. So the rate of glucose uptake can be assumed to be zero order. The rate constant is K0 at a yeast density in alginate of 15 weight percent. The rate constant there, the K0 there, is 0.5 grams per liter per minute. For maximum reaction rate, the concentration of glucose inside particles should remain above zero. What are the maximum particle sizes for glucose concentrations between 5 and 60 grams per liter? For 30 grams per liter of glucose, plot R max as a function of cell loading between 10 and 45 weight percent here. So we've got two different things. We're considering particle sizes here, and then we're considering different amounts of cell loading in the second part. So we can first think about the effective diffusivity at a yeast concentration of 15%. So simply enough, we just plug in YC in this equation here to get our DAE, and we find that we get at YC equals 0.15 or 15%. The DAE is 5.25 times 10 to the negative 10th meters squared per second. Now we will consider our maximum particle size per glucose concentration. So we have our yeast concentration, 0.15. We have our effective diffusivity. Let's convert our K0, our zero-order rate constant, to units of kilograms, meters, and seconds. That gives us 8.33 times 10 to the negative 3 kilogram per meter cubed second. So we'll assume CAS, our substrate concentration, is equal to the bulk glucose concentration. Determine our max, our maximum radius, using the equation to the right here, this equation here. A fairly simple equation, the square root of 6 times DAE times CAS divided by the rate constant. And then we will plot our max as a function of glucose concentration. So this is pretty easily done if we can consider a variety of concentrations here from 5 to 60, as we were told to do. And here is our plot of R max. You can see R max gets bigger, gets longer, the more glucose we have, the larger the CAS is. And this is not a surprise. So now for 30 grams per liter of glucose, plot R max as a function of cell loading between 10 and 45 weight percent. So as YC varies, which it is in this case, the values of our effective diffusivity and our first order rate constant K0 are affected. So we calculate our DAE, our effective diffusivity, and we can put together a chart that has the different values depending on the different yeast concentrations. And we are assuming our K0 is proportional to cell density as described in this equation here, where we have K0 equals our K double prime 0, where that is the specific zero order rate constant, and the YC, of course, is the cell concentration again. And we calculate our R max as before. So we have our K0 here, and we have our R max. And then we can plot those as a function of cell loading. And we can see that as the yeast concentration goes down, the R max goes up, the R max gets smaller, or can get smaller. So what did we learn by all this? As YC increases, our effective diffusivity declines, and our first order rate our zero order rate constant increases. Reducing the effective diffusivity lowers the rate of diffusion into the particles, and increasing the K0 increases the demand for the substrate. So with DAE on the decline and K0 on the increase, we need to have a smaller R max here, and you can see that clearly in this graph here. So increasing cell density basically exacerbates the limiting effect of mass transfer on reaction rate. And this is not a surprise. The diffusion is going to have to encounter more cells, which is going to cause some sort of impediment to diffusion. And we want to ensure and we want to have an adequate supply of substrate under these conditions. So the particle size must be reduced in order to keep the supply adequate. If we have too big a particle, we end up with the interior not receiving any substrate, and then no reaction is taking place. We have thus far considered spheres, and those are nice, but there are other shapes to consider. There's not just spheres, as I've been talking about. There are often flat plate geometries here, and these, instead of thinking in terms of radius, we think in terms of the width of the plate. Usually plates are attached to some non-porous solid, and we consider the concentration of substrate coming from the bulk liquid going into the flat plate, into the porous flat plate, and it looks an awful lot like the concentration gradient that we saw previously, where it's highest at the surface near the bulk liquid and lowest towards the surface of this non-porous solid. And we have concentration profiles that we can consider here if we're thinking about flat plates. We just change some of the variable names, as it were. We have spheres that have, and we've seen this equation already, in a first order reaction we have big R, little r. With a flat plate we have Z, which is the distance from the non-porous support. And again, if we're considering steady state shells, we have a varying distance. That is either B or less. The B is the entire width of your flat plate. For zero orders, it looks a little bit different. Here's the sphere. Again, we're looking at the radii, the shell radius, and the overall radius with the flat plate. Again, we're talking about that Z and that B here. So we've got these different reactions, either first order or zero order, to consider here. If we're looking at concentration profiles of substrate that are affected by diffusion and effective diffusivity. Okay, so let us consider something that's known as the effectiveness factor. The effectiveness factor is the extent to which the observed reaction rate, and that is that reaction rate that we see in the bulk liquid of the disappearance of substrate, how is that different from this R star AS, which is the hypothetical rate where our concentration of substrate is equal to the CAS. Basically, everywhere in the particle, our concentration of substrate is equal to that concentration of substrate at the surface of the particle here. So we have that, the R star AS equation here in a spherical particle, which is essentially, you've seen this before, the volume looks a lot like the volume equation, and then we have the first order rate constant, if we're considering first order reactions in this case, multiplied by the concentration of substrate at the surface here. And then we can calculate our effectiveness factor, which is the observed reaction rate divided by that R star AS, and then we therefore get a ratio that tells us our effectiveness here. So one way to think about what effectiveness factor is that if you imagine yourself trying to pick up lobsters from a deep lobster tank, lobsters are going to crawl around on the bottom, and they might crawl around each other. They're going to often stay away from your grasping hands. You're only effective at picking up lobsters if you can reach down to the bottom of the tank. If lobsters, however, are distributed evenly throughout the depth of the tank, if they're resuspended in jello or something, then you wouldn't have to reach so far down, and you could theoretically be more effective at grabbing them. So again, if you reach into the tank 10 separate times, and the tank's got water and lobsters in it, and you pick up 6 lobsters, your RA observed is 6. If lobsters were suspended in that jello, like I said, and thus evenly distributed, you can reach into the tank in 10 separate times, and each time pick up a lobster. 10 separate times, 10 lobsters. This is your R star AS. Your effectiveness factor at picking lobsters, therefore, would be 6 divided by 10, or 0.6. So in summary, heterogeneous reactions involve gradients, temperature or concentration gradient. We are basically going to talk about concentration gradients. These gradients occur when we have immobilized enzymes or cells. In a catalyst, the boundary layer immediately surrounding that spherical or that flat plate catalyst sees a decrease in the substrate concentration due to pore mixing. The true rate of reaction at the catalyst surface is difficult to measure. The observed rate that's going on in the bulk liquid, or that we're seeing in the bulk liquid, is much easier to measure, and they are probably not the same. Effective diffusivity, or DAE, as we've been talking about, takes into account the amount of space within the pores of the catalyst and the tortuosity of the pores. The effective diffusivity basically takes into account diffusion effects, as it were. First order reaction rates depend on the amount of catalyst present. Zero order reactions will proceed as long as substrate is present. In the case of immobilized cells, bulk biomass may affect diffusion, which will affect reaction rate. We'll talk a little bit more about this concept when we talk about biofilms, diffusion of biofilms. Effectiveness factor compares observed rate of reaction to a hypothetical rate where our concentration of substrate is equal to that concentration of substrate at the surface of the particle. So to read further, look at, if you've got the yellow book, look at it. Chapter 9, Section 9.4, pages 263 to 276. And hopefully I will see you on Wednesday, and we can continue normal operations. And just as a reminder, please watch this. Obviously, if you're listening to me say this, you've already watched it. So good for you. This stuff is probably going to feature heavily in the exam. See you on Wednesday.